All right, test to test again. So can you hear me? Okay, good. All right, so I think we can get started. Okay, so all right, good evening. Let's start with the topic here. Let's do a very quick review of what we did in the previous lecture. There are two components, two major components we covered. One is the concept of curl. And the other one is the Green theorem, which will come to that. Okay. So we spent a major portion of the previous lecture on interpreting the meaning of a curl. So the formula for curl is basically del cross F, and it's cross product. So we have the formula. I think in terms of computation of the curl, right, it's nothing, right? So everybody, as long as you have the formula, you can calculate the curl. It's mostly about how you actually interpreted this calculation of the del cross F. So I listed a few bullet points here as more of a remark from the lecture notes. So let's read it together. So the curl of the vector field F yields another vector field. So the aim, it gives you another vector. And the vector has two components. So it's a vector measure of a circulation, which gives both the circulation of the vector field F at that point and the direction of maximum circulation per unit area in the field. Okay. So if you have a certain location inside a vector field, and then you calculate this curl of the vector field, then it must be pointing to that direction, okay? And now, basically, at that location, you have this direction give you the maximum circulation, and the magnitude of this curl give you this the magnitude of the circulation, right? So that's where the curl basically given to you. Okay, and you also need to understand this is a microscopic calculation. So it's a calculation at a point inside the 3D space or inside the 3D vector field. Okay, so it's not a macroscopic. So we actually will come to that. The Green theorem is more of a macroscopic circulation concept. Okay. The last bullet is to reiterate what's the two components, the vectors. Okay. And then from here, we learn a new Green theorem. Okay. So Green theorem says, if you have a curve C, okay, we said it's positive oriented. So positive, you're looking from the top, it's counterclockwise view from the top. And then it's a closed curve, right? It's placed in the vector field F. If you're required to calculate the vector line integral over this curve C, then now you have an alternative method or approach is to calculate this double integral to give you the same result as this vector line integral. So Green theorem basically give you a relationship between vector line integral and a double integral, right? Now, a little bit deeper understanding the Green theorem is that this component of the integrand here for the double integral, it's curl F dot k hat, okay, and then dA, okay, dx dy dA. So essentially you're integrating is a curl F dot k hat, which is this integrand right here, right? Now, if you recall, okay, also in the previous lecture, we covered a concept called circulation density. So when you use the curl F dot k hat, so technically when you use curl F dot n hat dot any direction in 3D space, then you get, right, the n hat, let's say maybe pointing this way, right? Then you get the circulation density in that direction given by n hat. So this gives you a circulation density concept. Okay. So now you use a curl F dot k hat, so you get the circulation in the k hat direction. And because it's a 2D vector field, so curl F is actually just a vector pointing in the k hat direction or in the z-axis direction. Okay, so there's no other direction for the curl F. It's all in the same z-axis direction. So now this Green theorem, the right side of Green theorem basically becomes you're integrating circulation density over the region given by the R. So it's like you're adding up circulation density as this little diagram showing it here. So you have so many circulation densities within this region R enclosed by curve C. And when you add up all the small circulations within this region R, then you get the total circulation over this curve C. And that's basically what Green theorem is telling you at here. Okay. So you essentially you have a microscopic circulation given by the circulation density, and it relates to the macroscopic circulation over this whole boundary curve C. Right, so there's a connection at here between the microscopic circulation, right, those green ones, and the macroscopic circulation over the curve C. And as we later we're going to learn Stokes theorem, that's actually going to be in the 3D space. Okay. This one, Green theorem, rather is in plane. Okay, it's an in plane case. It's a 2D. Okay. So let's look at an example for Green theorem, and then we can get on to a different topic. So let's say I have a vector field given by this particular. So here's a vector field, and curve C is a unit circle at 2, 0. Okay. So it's a circle centered around 2, 0. It's unit, so the radius of the circle is 1. Okay. So now the question is can you calculate the vector line integral over the curve C? Okay. Obviously, I'm not asking to calculate the actual vector line using traditional approach, and we're going to practice to do this calculation using Green theorem. Okay. Yeah. So Green theorem says for this vector line integral, okay, you can calculate this double integral. Right. So the relationship is that this is your m, this is your n. Is m component for the vector f. This is the n component for this vector f. And the R at here, right, is the region enclosed by the curve C. So C is a closed curve, give you this region R. And that's the connection between these two. So once you get this connection, then we need to calculate two partial derivatives and then plug it into this double integral. Here's your function n, and here's the function m. If I calculate partial n over partial x, then you're treating everything else as a constant. So the partial derivative for this function, you get 2x, not 2x, you get what, x, because 2 cancel the 1/2. And then this is e to the power negative x. So partial derivative, you get become positive. So x plus e to the power of a negative x. Right. So this is your partial derivative, partial n over partial x. Partial m over partial y. So you treat e to the power negative x as a constant, and you get just e to the power negative x, and then dx, dy. Now, you simplify, you get just x, and then dx, dy, or dy, dx, doesn't matter. Okay, so it's basically, right, it's maybe just, let's write a dA for now. Okay. Okay, so everything else is simplified to this double integral. Yeah. Now, then from here, right, then you had to make a decision, how do I compute this double integral? And you have literally two different coordinate systems to use, right? Cartesian coordinates or polar coordinates, okay? I mean, you look at this one, this is a circle. So chances are you should use polar coordinates, okay? However, if you try polar coordinates, means, right, the approach of a polar coordinate is you draw a reading line out of the origin, okay? And then look for the first contact, second contact to give you the R min, R max, right? But if you look at the current drawing here, are any one of the R min or R max be constant? If you draw the arbitrary reading lines, if you look at the lengths for R min, the lengths for R max, or the lengths for the first contact, the lengths for the second contact, neither of them are constants, right? So whenever you have a case like this, and if you recall, then chances are you have to find a relationship between these R limits and the theta. But it's still very difficult. You know, you can try, but I don't think you can find one. So here's what I want you to expand your thinking here. So what would you do if this doesn't work to directly apply the polar coordinate? Yes. Shift to origin. Okay, excellent. But there's a name for this. We have a method, a name for the method, right? What's the name for the method? Change variables. Okay, so this circle here is x minus 2 squared plus y squared equal to 1. Very good. So this circle, if you directly apply polar to it, it's almost impossible. However, if you let u equal to x minus 2, then and v equal to y with a change variable, then your circle is shifted to the origin. And now you can safely apply your polar coordinates, okay? And you get a very easy solution. Okay, so that's the idea of change of variable. So I want you to try it yourself, okay? I'm going to actually give you a slightly different approach. Okay? And this is not a generic approach. The change of variable probably works more generic in many other situations. But I want to give you a slightly different approach. Okay? This one just because what we have here, I happen to be able to use what we're going to do. So now, if you recall, one of the applications for double integral is to calculate the center of the mass. And the formula for that is 1 over the mass, and then integrate over r x times the density, and then dA, right? So this is the formula for calculating the center of mass, just the x component of the center mass. Okay. So if you let delta equal to 1, then this formula becomes x equal to 1 over, instead of mass, it's actually become just the area of the region R, and then integrate over R, and then x dA. Okay. So by doing so, you can see, well, this is exactly what we're looking for, right? So this term here, that's what we're trying to calculate. It showed up in this center of mass formula. Okay. So which means this double integral basically equal to the x bar times the area of the region R. And this is under the condition that density is a uniform distributed, which is 1 across the whole region R. So go back to this region R here. Can you tell me where x bar is? 2, right? Can you tell me what the area of this is? Pi r squared. So everything is so easy. So this is basically 2 times pi r squared. R is 1, just pi. So end up just 2 pi, right? So that's an alternative approach, a little bit sneaky. So it doesn't really necessarily mean you can use this all the time. But if you see this, of course, then you could try, right? Especially if you have a very regular, like a circle or rectangle, so you can identify x bar, right, without even have to calculate. Okay. So that's this question, but I want you to try this change a variable approach, and you will get exactly the same answer as 2 pi. But overall, you can clearly see the idea of a green theorem. So essentially, you're trying to get away from calculating this vector line integral, and instead, you're calculating a double integral. Now, which one will supposed to save you more time or computation? Hard to say. You know, sometimes the double integral is better than this one, but sometimes this is better than this one. So, but either way, it should. If you are required to calculate both sides, then you should get the same result. Right. Okay. Any questions before we move on to a new topic? Yes. Is it 2 pi or pi? It's 2 pi because this is region R, so the center x bar should be right here, right? X bar should be right here, so that's 2. So x bar equal to 2. And area equal to pi r squared. The radius of the circle is 1, so that just end up the pi. Yeah. Okay. So now next, I'm going to talk about surface integral. Okay, this is a relatively bigger topic. Now, one thing that I also wanted to point out is, okay, many things from here on, actually from a couple lectures before this one, you feel like they're definitely new topic. But if you look at each one of the computation, you'll realize actually they're not new at all. Okay, so they're just combination of everything that we have learned, including what we're going to talk about the next, surface integral. Before we talk about surface integral, and I want to talk a little bit about the concept of flux. Flux. And you probably have learned a little bit about flux in 178, okay, electrical magnetic system. Let's talk about flux more of in a generic sense first. So what is flux? More generically, you will see flux is the amount of something, okay, passing through a surface in unit time. Okay. This is more of a lay language for the concept of flux. Amount of something, we didn't see what the something is. So the something could be anything passing through a surface in unit time. Okay. So the something could be electric field, could be magnetic field, or could be even bananas or fruits, whatever, right? So that's more generic something. Okay. Passing through a field, I'm going to show you a graph, in unit amount of time. If that thing passing through the surface very fast, then you get more passing through it, right, in unit time. If you have a bigger surface, then you also catch more, right, of that passing through the surface. Okay, so there are different things different factors playing at it here. So we'll come to that. But that's basically what flux is, right? Yeah. So not just the electric field or magnetic field, it could be anything. Now in civil or mechanical, right, there's a concept called transportation flux or transport flux. In examples of transport flux, for example, you have so-called heat transfer. You also have a concept called mass transfer. Okay. So in this transport flux concept, okay, it's essentially give you an expression at the end is you have a quantity okay, and then times time inverse, and then times area inverse, okay, times this time inverse and area inverse at here. Okay, so essentially, if you look at if I replace the quantity, right, replace the quantity with heat, then you get a heat flux. A heat flux, you look at the overall expression. So you have a heat, time inverse, area inverse, and the first two, right? Whatever divided by time, you have a quantity divided by time. That's a rate of change, right? That's a rate of change concept. So then you get essentially the rate of heat flow. Right? The rate of heat flow, that's purely based on the first two units. And then last unit is per unit area, right? Divided by area. So then you get the rate of heat flow, okay, across a unit area. And the unit of this is usually joule, meter per second, and then per meter square, and then per second. Right? So per second is time, per meter square is this one. Joule is the heat. So you get this heat flux unit. So similar, you can also get mass flux. Okay. How much heat is being transported, how much mass is being transported through a certain surface in unit amount of time. And that's physics. Now in this class, we're dealing with a mathematical description at here, right? Not just specifically certain physical phenomena. So in this class, the flux, okay, as a surface integral. So in this class, we're looking at is surface integral, and the result of that, we call it a flux. So basically what we're going to present and next, which will be a surface integral, and we use that, okay, as a description of flux. Okay, yeah. So that's what we're going to cover in this class. All right, so now let's do a more bigger picture illustration, right? Yeah, of understanding the flux first. I bet you have watched this animation, Cloudy with a Chance of Meatballs. So it just, a miracle happens, meatballs and other yummy stuff falling off the sky, right? So here's a simple question for you. Suppose you have a bowl, okay? And you have a choice to pick up a bowl. And your ultimate objective is to catch as much meatballs as possible, right? So this is you have a degree of freedom and you have objective. So can you give me some factors so that you can catch as many meatballs as possible? What are the factors playing at here so you can catch as much meatballs as possible? Okay, so somebody's already saying, okay, a bigger bowl, huh? Yeah, what else? I see a hand raised up over there. Speed. So you observe first. You observe what speed? The speed of what? The meatballs, right? Good. So you sit there. Let's see which part of the area has the fastest speed of the meatballs falling off, right? And then you go and catch over there. You don't catch it underneath the roof, right? Good. So speed. Speed means it's the vector field, right? And then the size of the bowl or the surface. So let's write down here. So you get the speed of the F, and you get the size of the surface. Okay. What else would you think of that you can, or trick you can play so you can actually catch more meatballs? Time? Yes, time definitely is a factor. Okay, but let's say if I'm looking for a more of ideal situation, unit amount of time. So everybody has equal playground, right? Yes. Sorry? Direction. Excellent. Direction between what? Direction between each meatball. And well, I guess you cannot change the direction of meatballs. Some meatballs falling this way, and some meatballs falling this way, right? And some meatballs falling the other ways, right? Yeah. But what would you do if you, yes? Exactly, right? You don't just hold the ball like this. You have a degree, you can orient it. So what do you think you should orient your surface to so that you can catch more meatball? That's right. So you want to orient your surface to line up with the falling of the meatballs. So then you can get more of that. Right. So the third is the orientation of surface. The orientation of surface and meatballs. Okay. Yeah. So these are the three major factors, right, that will give you or determine how fast you can catch, or basically it's the flux concept, right? Like what we did in the beginning here, the amount of meatballs passing through the surface in unit amount of time, right? Yeah. So this is all good, but we do want to calculate this mathematically, right, in a more systematic way. So let's take a look at how we can formulate all of the three things into one single formula, right? Okay. Before we proceed, this is actually illustration of what we have just described. Now, if you have a ring which represents, let's say, a unit area, and then the lines over here represent a vector field, right? So obviously, the more lines go through it, the more vector field goes through it, right? The more amount of a flux. And orientation in the ring also affects how many lines, how many vector field lines will go through it, right? And also the intensity of this vector field, right? And is also a factor plays that determine how much flux is going through it, okay? So before we go ahead to do the formulation, so if I have a surface, which is the bowl that you're holding, then at each location on the surface, you can always draw a vector perpendicular to that surface. Okay, so what the drawing showing at here is a whole bunch of vectors perpendicular to the surface at their individual location. Okay, so what's this drawing here? So you basically you get a lot of unit vectors n hat, and it's perpendicular to the surface, right? Yeah. So that's what this drawing is showing here. So now, let me move down this a little bit here. So if I draw an arbitrary surface, and let's take a very small patch, a very, very small patch from the surface. Then at this location, you have n hat attached to it, which is perpendicular to the n hat, to the surface. At the same time, as we have illustrated, you may have a certain amount of something, okay, passing through this surface at that location. And we can use a vector f, okay, representing the direction of the something going through it at the location. Okay. So now, in a unit amount of time, then you got amount of something passing through that small patch, and you're creating this parallelogram. Okay. So the question basically is calculating the flux, right? Is how much is passing through this delta A in unit amount of time? And how much is passing through this little area delta A in unit amount of time is basically given by the volume of this parallelogram. Right, so because we're thinking in a very small scale, so and a small scale in terms of the patch, in terms of the F, so we consider basically the vector field is even over this delta A area, right? So that this is how we create this parallelogram based on this delta A. And of course, if F is traveling faster than your unit amount of time, then this vector line probably is a little bit longer, right? Otherwise, it's a little bit shorter, right? But overall, right, so if we're looking for is the flux or the amount of something through this delta A in unit amount of time, then it's this volume, okay? So let's calculate the volume, right? So basically you get a delta flux, okay, which equal to the volume of this object that here. The volume equal to the base area, back to our first lecture, if you recall that second lecture. When you calculate the volume of a parallelogram, what is what? It's the base area multiplied by the height. What is the height then? What is the height? F. How do you get the height? You have F, you have n hat. Exactly. F dot n hat, right? And thank you very much. So this is the volume of this parallelogram. F dot n hat give you a delta flux. Right? That delta flux is the flux through this delta A. What you're looking for is the total flux over the whole surface, or the total something passing through that surface. So what you do, you basically add up all the small delta flux, then you get a total flux, right? So now where we're gonna get is the total flux equal to you're adding up this whole this term here, or this quantity here, this delta flux. So what are we adding? We're adding up this F dot n hat, and then delta A, right? When you add things up, you're doing integration, right? Summation becomes integration, and you're integrating over the surface, and then the delta A becomes dA. You get the total flux. Right, through this simple analogy here, we have, okay, so this is the surface S. So we have a double integral showing up at here. It's integration or summation of small flux, okay, over the delta A patch, give you a total flux over the whole surface S, and which is what we call the flux. Okay, so flux as surface integral. Okay, now you will see why this is a double integral. Okay, because we're dealing with a dA at here. It's a integration, right? dA is a small patch. So when you're integrating, not integrating over region, then you have double integral. If you're integrating over region dV, then it becomes triple integral, right? Yeah. So here is a double integral concept. Okay. So if you look at the equation showing at here, does this equation actually cover the three factors that we have discussed here, the three things, right? If you look at the three things, what affects the flux, the speed of this, or the size, basically information of the vector field, size of the surface, and orientation of the surface versus this meatball, or meatball here is the F. So if you look at this formula here, S is right here, right? The bigger S, you get more flux. And F is right here. The intensity of the F will affect the total calculation of flux. And relative orientation relationship between F and n hat is given by the dot product. Because if you look at this, what is actually going through the surface, right, is F, projection of F in the n hat direction. And that's F dot n hat. That's what really matters, right? So this equation essentially captures all of the three discussions that we have illustrated, right? To give you this calculation of flux. Of course, the next question is, how do we calculate this thing, right? So that's what we're gonna talk about in details, okay? Now, before we look at the calculation of this surface integral, so this is called a surface integral, okay? And before we go ahead, and you need to understand this n hat is perpendicular to the S. Okay. And also, I want to be clear with one concept first, before we look at different approaches for calculating surface integral, basically under different coordinate systems. This concept is called orientation of surface. Okay, orientation of surface. So for any surface, okay, for any surface, if you look at one location on the surface, you always have two directions of n hat. So you always have two vectors pointing to completely opposite direction, 180 degrees opposite, perpendicular to the surface S. So that's why we see for any surface, right? There are always two directions of n hat, okay, at a point. Okay, so you will actually face the decision is, so which n hat should I pick for a particular calculation of a certain surface integral in a certain question? Okay. Now there's a little bit of the rule of thumb here is if surface is closed, right? So it's very possible. So you can have a, let's say for example, spherical surface, which is a closed spherical surface, or maybe a box, right? If this surface is closed, then our flux is considered as positive. So, or in other words, our n hat is positive. Okay, yeah. So if you're required to calculate, you watch the question. The question says, calculate the outward flux, right, out of a certain surface S. Then when you pick n hat, okay, for that surface S, you need to pick the outward n hat. Okay? So because there are always two directions, right? A positive and negative difference. So that's something that you had to keep in your mind, right? When you read a question, because okay? You do have two options for n hat. All right. So now let's formally look at evaluations, okay, of this surface integral. So grab a piece of paper and write a few times of this formula, okay, integral over S f dot n hat dA, and also talk to yourself, what is f, what is n hat, what is surface S, what is relationship between S and n hat. So then that formula will become yours, right? And the first, we look at probably 3 or 4, actually 4 different cases. The first case is using a spherical surface, okay? So basically, if you have a surface happen to be a spherical surface, or maybe part of the spherical surface, that's the S over there, then how do we deal with this surface integral? Okay, so that's what we're going to look at. So let's look at this case here. So what I draw here is a generic spherical surface, and it's a whole spherical surface centered around the origin. Okay. Then remember, we're talking about this surface integral. So it's different from a triple integral. Okay, so when you do triple integral, you're actually going through the whole region, right, enclosed by the surface. But when we do surface integral, okay, we're integrating over the surface, in this case, a sphere. Then typically, if you have a spherical surface or region doing triple integral, if you recall that, you have a rho phi theta, right, to deal with the triple integral. Okay, but however, because for under this case here, we're just integrating over the surface, so we don't need 3 coordinates here. Because why? Because the rho, which is the definition of a distance from origin to a certain point in 3D space, if I pick a point on the spherical surface and then creating the rho, right, pick any point on a spherical surface. So the rho is actually what? constant. Right? It's the radius of the sphere. So I don't need to worry about the rho because this is a constant, right, under this case number 1. Okay. So I just had to worry about the phi and theta, these two variables, to enable us to calculate this surface integral. Okay. So here's what we're going to do. So we're going to look at what will be an expression for this dA, okay, under a spherical surface. And what it will be an expression for the n hat. Okay, so slowly to find the overall expression for this surface integral. dA, so this is what we did. We create a little patch on the spherical surface by using longitudinal circle and the latitude circle to create this little patch. Okay. Or you could also consider this way is how the little patch is created, right? You see the two red or longitudinal circle essentially is a rotation from theta to the next one by a delta theta. Okay. And these two circles here, right, essentially is a rotation from phi to the next level by a delta phi. Right? That's how you created this little patch. And then using approximation concept, because it's very small, so we can consider this as a rectangle box. So I can calculate the little area of this little patch. The calculation of this little area, okay, by basically multiplying two sides together, and you get a square sine phi, okay, and d phi d theta. So one side multiplied by the other side, and you get this dA here. Right? When you look at this dA, I think if you jog your mind, if you recall, under spherical coordinates, what is the expression for the dV? Rho square sine phi d rho d phi d theta. Right, that's the expression for dV for triple integral under spherical coordinates. And if you compare these two at here, because we had stated just a moment ago, because it's a surface, so rho is actually constant. It's a radius, so rho is radius A at here. And you don't have to worry about the d rho because you're not integrating over the d rho direction. So you only left with a squared sine phi d phi d theta. So that's your dA. Okay, yeah. So this step here basically gives us the expression of dA in terms of the spherical coordinates phi and theta. Okay. So the next thing is, what will be this n hat? Okay, what will be this n hat? This n hat here. So go back to the original definition. N hat is a unit vector perpendicular to the spherical surface. Okay. So we need to find a unit vector perpendicular to this spherical surface. What will be the candidate for a unit vector then? Right. So let me draw this spherical surface again, and here, and then it's not as good as the other one. So let's see, I need an n hat at an arbitrary location, right? Yeah. So let's see if something makes sense or not. If I pick this point P, and the point P has coordinates x, y, z, right? Yeah. So what do you think if I connect from this origin to this point P? If I connect from origin to the point P, and creating a vector OP, what will be the relationship between OP and the surface of the sphere? Yes? No? So you have outside is a surface of sphere, and you create basically OP to the surface. Yes. Huh? Normal, yes, perpendicular, right? So it's like you have a reading lines from origin going all the way out, and then you have a sphere right at a certain layer of a certain distance from origin. So the reading lines is certainly or guaranteed to be perpendicular to your surface. Right? If you recall in this 2D case, for example, right? If I have a circle, if I pick a point at here and I'm creating a vector like this, what do you think this vector? This vector must be what? Perpendicular to the tangent line at that location, right? And perpendicular tangent line is equivalent to say this vector is perpendicular to this outer circle. So same idea over here. If I create a vector OP, and OP will be perpendicular to the spherical surface. Okay? So OP are obviously equal to X, Y, Z. And guaranteed that OP is perpendicular to the spherical surface. Good. So now let's look at this OP here. So OP is this vector. I'm not looking for OP. I'm looking for a unit vector, n hat. So then the n hat could be just normalize this OP. You normalize the vector, you get a unit vector. Normalizing this means X, Y, Z on the top, the magnitude on the bottom. So that's n hat. A magnitude at the bottom, right? So magnitude, what is the magnitude of OP? Radius. So it's 1 over A, X, Y, Z. So n hat is basically 1 over A, X, Y, Z. Now, of course, we have mentioned that for any surface, you can have two directions of n hat. Pointing outward in this case and pointing inward. So technically, right, we can add a positive and negative in front of this vector. So we do have two directions of n hat. So now we got n hat. However, right now, if you look at the n hats and the dA, okay, they're not very compatible because dA is written as the spherical coordinates phi and theta. And n hat is written as the Cartesian coordinates x, y, z. So I want it to be compatible. So I need to change this x, y, z into the spherical coordinates. So what do? Right? It's quite simple. You recall the three expressions for spherical coordinates. You have a rho, sine phi, cosine theta. But now you don't have a rho anymore. You have a constant a. So x is basically a times sine phi cosine theta, and y equal to a times sine phi sine theta, and z equal to a times cosine phi. So any coordinates on the surface of sphere, and this is x, y, z, refer to a point P's coordinates on the surface of sphere, is related to the spherical coordinates theta and phi through these three relationships. Okay. So finally, we can summarize basically the formula for this surface integral. Okay, so let me just quickly finish this. Okay, so you have this f dot n hat dA. F is, let's say F is a 3D vector, M and P. And n hat is 1 over A, X, Y, Z. And the A is A squared sine phi, D phi, D theta. Okay. And you look at this expression in here. So M, originally M must be a function X, Y, Z. So is N, also, and so is the P. So what do I do then? For all of the x, y, z involved in this expression, you need to substitute, replace them with the three expressions at here. So you need to replace all of the x, y, z involved, okay, in this surface integral with the three expressions. So you get rid of all of the x, y, z, and everything else turn out to be in terms of a phi and theta. And the next lecture, we'll look at how do we find the limits for phi and theta. And then we can calculate this surface integral. All right. So, okay. So let's just do that and look at examples in the next lecture. All right. Yeah.